Department of Physics, which was established in 1958, presents St. Joseph's massive open online courses on the topic optics as skill effective course. Myself, Dr. C.H. Praveen Babu, Assistant Professor, Department of Physics, St. Joseph's College for Women Autonomous, Vishakhapatnam, Andhra Pradesh, India, as a skill effective course on the topic optics. The subtopic is Chapter 4 Polarization. In this topic 4.5, Laurent's half-shade polarimeter. Learning outcomes from this topic: student will understand principle of operation of Laurent's half-shade polarimeter. Components that are used here can be identified. Laurent's half-shade polarimeter. Polarimeters are the instruments designed to measure the angle of rotation produced by a substance. When they are calibrated to read directly the percentage of cane sugar in a solution, they are named as saccharimeters. Polarimeters can be used to find specific rotation of sugar solution, or if the specific rotation is known, they can be used to find its concentration. These are the different models of Laurent's half-shade polarimeters that are used for testing this method. Construction of Laurent's half-shade polarimeter. The essential parts of a Laurent's half-shade polarimeter are as shown in the figure. S is a monochromatic source of light and L is a convex lens which renders the incident light into a parallel beam. Here N1 and N2 are two Nicol prisms. N1 acts as polarizer while N2 acts as analyzer. N2 is capable of rotation about a common of N1 and N2. The rotation of analyzer N2 can be read on a graduated circular scale. The verniers are also provided to read the fractions of a degree. Light, after passing through the polarizer, becomes as a plane polarized with its vibration in the principle of plane of Nicol N1. The plane polarizer light now passes through a half shaded device and then through a tube T containing the optically active substance. Here we are taking the sugar solution. Actually, N is a hollow glass tube having a large diameter in the middle so that no air bubble may be in the path of the light when filled with the sugar solution. This tube is closed at ends by overslips and metal covers. The emergent light on passing through the Nicol prism N2, which acts as an analyzer, is viewed through a telescope. The telescope is focused on the half shade. Action of half shade. When an optical active substance is placed in between two cross Nicols, the field of view is not dark. In order to make the field of view dark, the analyzer is rotated. It is observed that when the analyzer is rotated, the field of view is not dark for a considerable region. Hence, the measurement of optical rotation is not accurate. To avoid this difficulty, a half shade device is used. The Laurent's half shade plate consisting of semicircular half wave plate ADB of quartz material cut parallel to the optic axis so that it introduces a phase change between the extraordinary and ordinary rays passing through it, and a semicircular glass plate ACB as shown in the figure. The two plates are cemented along the diameter AB. The thickness of the glass plate is such that it absorbs the same amount of light as the quartz plate. Let the plane of vibration of the plane polarized light incident normally on the half shade plate be along PQ. Here PQ makes an angle theta with AC. The vibration emerge from the glass plate as such, that is along the plane PQ. Inside the quartz plate, the light is divided into two components, that is one ordinary component along x dash as shown in the figure, and the other extraordinary component parallel to the optic axis, that is y dash axis. The two components travel along the same direction but with different speeds. The ordinary component moves with greater velocity than extraordinary component, and on emergence a phase difference of pi is introduced between them. Due to this phase difference, the direction of ordinary component is reversed, that is, if the initial position of ordinary component is represented by OM, then the final position should be represented by ON. Now, the resultant of extraordinary component OL as shown in the figure and the ordinary component ON will be OR, making an angle theta with y-axis. Thus, the vibration of the beam emerging out of quartz will be along RS. If the principal plane of analyzing nickel is parallel to PQ, then the light from the glass portion will pass unobstructed while the light from quartz will be partially obstructed. Due to this fact, the glass half will appear brighter than the quartz half. On the other hand, if the principal plane of the analyzer is parallel to RS, the light from quartz portion will pass unobstructed while the light from quartz will be partially obstructed. Thus, the quartz half will appear brighter than the glass half. If, however, the principal plane of analyzer is parallel to AC, that is y-axis, it is equally inclined to the two plane polarized lights, and hence the field of view will be equally bright on both quartz and glass plates. Thus, the half shade serves the purpose of dividing the field of view in two halves. When the analyzing nickel is slightly rotated from this position of equal brightness, a marked change in the intensity of two halves is observed. Determination of specific rotation. We know that the specific rotation S is given by S is equal to theta by L into C, where theta is the angle of rotation measured in degrees, L is the length of the solution measured in decimeters, and C is concentration of solution measured in gram per cc. Hence, to determine the specific rotation of a substance, solution of known concentration is prepared. The length of the solution is measured directly. The value of theta is determined as follows. First of all, the experimental tube is filled with water and placed in its position. The telescope is focused on the half shade and the analyzer is rotated till equal bright position is obtained. The readings of the two verniers are noted on the circular scale. Now the tube is filled with optically active solution already prepared, that is sugar solution, and placed in its position. The field of view in this position is not equally bright. The analyzer is rotated and is brought to a position so that the whole field of view is equally bright. The new portion of two verniers are again noted on the circular scale. The difference of the two readings of the same vernier gives the angle of rotation produced by the sugar solution. The experiment is repeated with different concentrations of solutions. A graph is then plotted between concentrations and the angle of rotations. This comes out a straight line. From the graph, the ratio of theta by C is determined. Substituting these values, the specific rotation is calculated by using the above formula. Strength of sugar solution. To find out the strength of the given sugar solution, the experiment is performed in a similar way as to determine the specific rotation, that is, theta and L is found. The specific rotation at the temperature of the solution is found from the table of constants. The concentration of the given solution is then calculated from the formula. C is equal to theta by L into. Applications of Laurent's half-shade polarimeter. Determining the concentration of optically active substances. Analyzing the purity of substances. Identifying anemometers and stereosmers. Quality control in industries like pharmaceuticals and food. In this topic 4.5, Laurent's half-shade polarimeter, what have we learned? Students understand how to determine the angle of rotation. Students able to explain the applications of Laurent's half-shade polarimeter. Students understood the concept of specific rotation. Thank you.